When we connect our computer to the network today, we're usually using Wi-Fi for wireless or Ethernet for a wired connection. Ethernet is by far the most widely used link layer mechanism in the internet today. So the link layer covers how an end host is connected to a router, how one router is connected to the next, and generally, as we've seen, packets at the IP layer are encapsulated into a link layer frame, most often Ethernet, in order to be sent off to the first router. So in this video and the next, I'm going to be describing something called CSMA CD, which is right at the heart of how Ethernet works, and was very much a part of the original Ethernet. And I'll be describing how Ethernet started out, its evolution over the years, and then how Ethernet switching became a very common way to extend the scope of a link to cover many, many end hosts connected to a single router. You'll often hear Ethernet referred to as layer 2, and this goes back to the 7-layer OSI model that we saw in an earlier video. Whereas in the 4-layer internet model, Ethernet is the lowest layer. In the 7-layer OSI model, Ethernet encompassed both the link and the physical layers, both of the lower two. So Ethernet is often referred to as layer 2 because of the link. The link really just covers the frame format and the algorithm that decides when a packet can be sent onto the wire. And we're going to see that a little bit later. That's the CSMA CD mechanism. The physical layer covers things like the connectors and the electrical signals that are used on the wire. Ethernet started out as a means to connect multiple computers together on a single cable. That single cable was arranged as a long string or a bus, as shown here. It was in fact a big thick yellow cable that snaked around either in the walls, the ceiling, or under the floor. And computers would be connected down into it. And then they're all sharing access to this same common wire. And the idea was that they would share it in order to be able to send packets between themselves, but that only one packet would be allowed onto the cable at a time, because otherwise it would collide or corrupt and interfere with other packets. So this is what we call sharing a medium, and Ethernet is an example of when multiple hosts share a common cable. That's what we mean by medium. So to share the medium, we need to decide who gets to send and when. Because if only one packet can be sent on the medium at a time, we need to decide when the medium becomes free, who is it that gets to use it next? Do they do it in round-robin order? Do they do it randomly, whoever gets to send first? What is the mechanism for doing so? And there's generally a class of what are called medium access control protocols, or MAC protocols. And these are the protocols or algorithms for determining who gets to send next. We're going to look at some examples, but one thing to note here is you've probably heard Ethernet addresses being referred to as MAC addresses before, and you may even see this written on the bottom of your computer. MAC stands for Medium Access Control, even though we'll see later Ethernet doesn't use this mechanism very much anymore. That's just a vestige of the earlier 10 megabit per second version of Ethernet. Let's take a look at some examples of medium access control protocols. There have actually been dozens or hundreds of them described, published, and invented over the years, and many of them were standardized. But because many of them have gone out of fashion, I'm really going to be focusing on just one, Ethernet, or Carrier Sense Multiple Access with Collision Detection, CSMA CD. That's the one we're going to be focusing on, but I just want to set it into context a little bit. So there are MAC protocols which are simple and random, the simplest of which is something called Aloha that I will describe in a moment. And at the other extreme is a method called token passing. Let me describe roughly how these work. Let me start with the simple and random mechanisms. A random access protocol is one where every host can try to send at any time that it has data to send. It doesn't need to wait for some central authority to give it permission or until its turn comes around. It just tries to send. It might listen and see whether anyone else is speaking, or it just may go right ahead. So it's random in the sense that it just may start speaking at any time. At the other extreme, deterministic protocols like token passing have some means to explicitly control who gets to go next. In other words, which host gets to send a packet next. The most common method is called token passing, in which a special packet or a token is sent from one host to the next. So they might be arranged, for example, in a ring. And there'll be a packet called the token that goes around. This would be the token packet. And when you hold the token, you're allowed to send a packet. So it might then send a packet on to another host. So this would be the packet being sent. And then when it's finished sending the packet, it then passes on the token to its neighbor, who then gets the opportunity to send a packet, and then will send the token on again. So the token will go around like the conch shell in Lord of the Flies, if you've read that book, or in any mechanism where we have a round-robin opportunity to send, and the token is indicating who gets to send next. This gives every host the chance to send in a deterministic order, but it does require us to both generate and maintain this token. And it turns out that there are lots of ways in which this mechanism can fail. And the token get lost, or the token can get duplicated. And so these have generally fallen out of favor and being replaced by the simpler Ethernet mechanism, in which every host just basically randomly sends, but we'll see how that's controlled using this CSMA CD mechanism in a moment. So generally speaking, random access protocols are simple to implement, give really good performance when there are a small number of senders sending data at random times, but they work less well under very heavy load because they can spend a lot of time colliding with each other and corrupting each other until they figure out an opportunity to send. So when we're designing a MAC protocol or choosing one, then we generally have some goals in mind. We would like to have high utilization of the shared channel. We like to make sure that most of the time is spent sending data, not trying to recover from collisions or when multiple end hosts are talking at the same time. We'd like it to be fair. We'd like it to be fair in the sense that everybody gets an equal opportunity to send, averaged over a long period. We'd like it to be simple and low cost to implement so that it can be very widely deployed. And we'd like it to be robust to errors. So we'd like it that if an end host fails, then the chances are it's not going to bring the whole network down. Let me start with an example. And the example that I'm going to be using is one of the earliest medium access control protocols called the Aloha protocol that was used in the Aloha network in Hawaii. So here are the Hawaiian Islands. Basically, there was a central station in Oahu where Honolulu is, and then there were relays or end attachments at radio transmitters on the islands of Kauai, Molokai, Maui, and Hawaii. And every packet that was sent would be sent from an end host into the central station, which would then rebroadcast it out to everybody. And so this was radio-based, RF-based. There was no wire, and so the medium in this case was the air. The way that Aloha worked was all hosts would transmit on one frequency. So if a host has something to send, it would send on, say, frequency 0. This blue is just representing the channel corresponding to frequency 0. This would be sent up to the main relay station, or the central relay station on Oahu. And then that would be retransmitted. The packet data would be retransmitted out over frequency 1, a separate frequency, so essentially a separate orthogonal channel that would then be repeated to all end hosts. So we need a way to decide who can send when. And for this, we need a protocol that everybody agrees upon so that the system will work correctly. And the first Aloha network used the Aloha MAC protocol, which is very simple. If you have data to send, transmit it. If your transmission collides with another, retry later. That was it. So very simple. You send, and then if you discover that it collided, then you would retry later. How do you know that it collided? Well, you would send on frequency 0, and you would listen on frequency 1. And if what came back was not a correct copy of what you would send on frequency 0, you know it must have collided, and therefore you need to send again. And you would retry at a later time. Nice thing about the Aloha protocol was it's very simple. It's pretty robust against the failure of an end host. What do I mean by this? Well, if an end host fails and just stops sending, then the mechanism doesn't rely on any end host being powered on or correctly operating, because it'll just stop sending packets. There is a failure condition if it just starts jabbering away, sending packets that are meaningless. It can actually bring down communication for everyone else. So that's why we say that it's quite robust against failure. The protocol is distributed. It's distributed in the sense that it's actually operating independently on all of the end hosts. They all independently decide for themselves. Under low load, when there are either very few hosts sending, or they're sending at a very low rate, they're sending infrequently, we can expect the delay to be small. Nearly any host that has data to send will find that the channel is free when it wants to send its packet. So it's very likely to get through first time with very little trouble. It doesn't have to wait for some coordinating mechanism. It just sends, discovers that it gets through, and that's great. Under high load, a lot of time can be wasted sending packets that collide, because under high load the chances are that there are other hosts wanting to send at the same time. And so as a consequence, generally speaking, the Aloha protocol is thought to have very low performance. And in fact, studies and theory and simulations have all suggested that under high load you can show that the wasted time is so high we can only achieve about 20% throughput. 18% in fact. So over 80% of the time is spent on transmissions that collide under very heavy load. Clearly we need to improve performance. There were many papers in the 1970s and 80s on this topic of how to improve networks like this. And the technique most widely adopted for wired networks is called CSMA CD, and it was used for Ethernet. And you can see some of the ideas here for improving performance. One is, instead of just going ahead and sending, regardless of whether anyone else is sending, you could actually listen for activity first. This is the carrier sense part of CSMA CD. So you listen, first of all, to check whether anyone else is sending before sending a packet. If they are, you wait. If they're not, then probably your packet will get through okay. The next one is to try and detect collisions quickly and stop transmitting. If you take your time to detect the collision, or you wait until the packet is over, then you've wasted all of that time. If you can detect it very quickly, back off, and then try again later, then you can improve the performance. And the third one is, after there has been a collision, pick a random waiting time that is based on the load. In other words, pick a random time before trying again. If the load is high, then wait a long time, because that'll give others the opportunity to be able to send. If the load is low, then wait a short time, because probably you'll get through successfully next time. If the load is high and you wait a short time, the chances are you'll collide again, and it'll just be a wasted opportunity. This leads us then naturally from that simple Aloha mechanism to the very widely used CSMA CD protocol. And this is how it works. So this is what was used for the original 10 megabit per second Ethernet. So all hosts can transmit and receive on the one channel, which is this wire here. This is the shared medium. Packets are a variable size, of course. When a host has a packet to transmit, first of all it does carrier sense. So that's the CS of CSMA CD. It checks that the line is quiet before transmitting, so it listens. If the wire is quiet, then it says probably my packet will get through. Then, if there is a collision, it will try and detect it quickly. It will detect the collision as soon as possible. If a collision is detected, it will stop transmitting, wait a random time, and then it'll go back to 1 again. In other words, it will go back, listen for whether the wire is quiet, and then try and transmit, and if there's a collision, it'll keep doing that. And it'll just keep doing that until it's successful. This random time is called a binary exponential backoff, and all it means is, as the number of collisions increase for a given packet, it will wait a longer time. In other words, if there are lots of collisions, it means there's lots of other transmitters, and therefore I should try and hold off a longer amount of time in order to be able to give everybody the opportunity to send. Let's look at how CSMA CD works in practice. Let's say that I have a packet at A that wants to go to D. So it has the Ethernet address of D. A will send the packet. The bits, the packet will propagate down the wire. So I'm going to draw it all the way along the wire here with D in it, as if it's moving from left to right. It'll propagate at the speed of light down the wire, and then it'll come up into D. D will recognize the Ethernet address, and the packet will be correctly delivered. That first bit that very first bit at the front of the packet will start out by being put onto the wire here, and then it'll propagate along, and it will take it L over C, if L is the length of the cable from A to D, it'll take it L over C seconds to arrive. D listens, here's the packet, and in the meantime, while that packet is coming in, the wire is busy, so B, C, and D will all hear the wire is busy and won't try and send packets. So if they've got anything to send, they will say, they'll do the carrier sense, the step one, say, the network is busy, I won't try and send now, I'll wait until later. Now let's look at the condition of what causes a collision in the network. So if A again has a packet destined for D, and D has a packet that is destined for A will send its packet. So let's look at the first bit. I'm just now going to talk in terms of the first bit propagating down the wire from A to D, and it'll take L over C seconds. If that packet is going down the wire, here is the whole packet, and D listens and says, aha, it's quiet right now because the first bit hasn't arrived, and starts sending its packet, and so its packet is heading down in this direction, its first bit is going down here, and so at some point that the front of this packet will collide with the front of this packet, and after that they will pass through each other, corrupting each other, so that everyone that sees it, first of all C will see it in this case, so it will hear that there is a collision. And the way that it detects the collision is through a number of mechanisms. One is it just starts to get garbled messages. It sees a much larger number of transitions, basically twice as many transitions on the wire, or the main frequency component is doubled, or the voltage level has been increased. Any of these mechanisms can be used to detect a collision. As the packet from D continues to head towards A, that collision will soon be noted at B when the front of the packet gets to B, and so it will hear the collision. And eventually that packet will reach A, and it will hear the collision. And of course, this packet here will hit D, and so it will hear the collision. So at all slightly different times, they all hear the collision, depending on the particular time that the packets were sent. So, carrier sense, listen, see whether the line is quiet, send the packet, listen for the collision, then back off. The binary exponential back off is set so that there's a good chance that they will both back off by different amounts and therefore not collide next time they send. CSMA CD networks have a minimum packet size requirement. Let me explain why that is. Going back to my example of when A and D were sending packets to each other, imagine now that A and D are sending packets on this network of length L and speed of propagation C. Imagine that the first bit of the packet from A, so remember we have packet from A to D, and we have packets from D to A. D listens, hears that the wire is quiet, and at time 0, so this is going to be t equals 0, the first bit of A from A is going to start propagating down here towards D. Now imagine that at a time, just a tiny, tiny little bit, L over C minus delta, just a tiny time period before that first bit reaches D, host D decides that it's going to send its packet. It listens to the wire, says that it's idle, and then starts to transmit its packet. So the packet almost immediately collides, and at time delta later, the collision will be detected at D, and D will stop transmitting almost immediately. Now, although D knows about the collision, A doesn't know about the collision yet because that information or that collision has not propagated to A. So that little fragment of what of D has sent will propagate down here. So this is the collision propagating down. And so eventually the propagation, the first bit will reach here. If A is still sending the packet towards D, in other words, if it hasn't reached the end of the packet yet, then A will detect the collision as well. And it will detect that collision after L over C from when it started, and then another L over C until the packet is finished. So there's 2L over C in the worst case is the time from when A starts sending a packet until it hears of the collision. If A had finished sending its packet by the time the collision propagated to it, A wouldn't realize that the collision took place, and when it hears about the collision, it wouldn't know what packet had caused the collision. Had it been its own packet? Had it been a packet from another host? So in order for a simple way for A to be sure that it stops and realizes that there was a collision, needs to back off and retransmit the packet, one simple way to do this is to make sure that A is sending its packet for at least 2L over C. In other words, in the worst case, it's guaranteed to hear about the collision before it stops transmitting the packet. This means that we have a requirement of P over R, the packet length divided by the rate, is greater than or equal to 2L over C. This is a general requirement for CSMA CD networks in order to be able to detect a collision while it's still transmitting a packet. Let's look at an example. Imagine that I have a CSMA CD network which is running at a rate of 10 megabits per second. And let's say it's 10,000 meters long, 10 kilometers long. It's a pretty big network, and that the speed of propagation is 2 times 10 to the 8 meters per second. Well, we need P over R is greater than or equal to 2L over C. So we can say P must be greater than or equal to 2 times L, 10 to the 4, times, well, I've just moved the R over onto the other side, so 10 to the 7, divided by 2 times 10 to the 8. So the 2's are going to cancel, and I've got 11 over 8 is 1,000 bits. So what that would tell me is that for a CSMA CD network to operate correctly at that size and those rates, the minimum size packet has to be 1,000 bits, or about 128 bytes. So in summary, we've seen how medium access control protocols are used, starting with Aloha, nice simple random access protocol, and then improved in its performance to create CSMA CD. And we saw that CSMA CD is very simple, nice random access mechanism, and we learned that the minimum packet size, P over R, has to be greater than 2L over C in order to be able to reliably detect collisions before we finish transmitting a packet. In the next video, I'm going to be explaining how CSMA CD was used in the original Ethernet, and then how Ethernet has evolved over time, and then end with Ethernet switching.